All right, hi everybody. Today we're going to talk about energy in the simple harmonic oscillator as well as simple harmonic motion and how that comes into play with constant circular motion. So first, I do want to remind you of a formula we've seen before. This is actually Hooke's law. So Hooke's law generally discusses the amount of energy that's actually present in an elastic situation. Think spring, rubber band, etc., etc. From there, we move into how does this matter when it comes to energy? And just like most situations we've discussed so far, energy is going to be conserved. So we're going to see that total kinetic plus total potential. In this case, we're going to talk about just elastic because we're talking about an oscillator. And remember that a lot of the times we simplify an oscillator to be something that bounces back and forth, right? And in our case, that would be a spring. So total potential plus total kinetic is always going to be conserved. Remember that conserved in this class means before and after the motion or the whatever may take place. To make that even more complicated, we insert our equations for the elastic potential energy and the kinetic energy in order to discuss exactly what does it mean when this energy is conserved. From there, we can also then talk about rotational analogs. So remember that for every translational variable, velocity, acceleration, etc., we have rotational versions. So in the previous slide, we have 1/2 kx squared. K is actually going to then be substituted in for mgl. X actually comes out to be theta. In this part, we have the linear analog for angular velocity is going to be v, and ml is actually replaced by mass in that previous problem. Okay, so our simple pendulum would be one of our examples of something that would have rotational quantities. Remember that pendulum that you hang from any point actually has one rotational point. That's why it's considered a rotation. Springs a little bit different. They may be attached to a single point, but they don't rotate, right? The motion of this guy is not this. The motion of this guy is back and forth only. All right, so that being said, then we want to look a little bit closer at what's happening from an energy standpoint in terms of how long it's taking for something to occur. So for here, we can look at the simple harmonic motion that we've seen on that previous slide by looking at the actual spring energy. Remember that the spring itself, K is a constant related to how thick the spring is or how springy the spring is, if you will. X is going to be the distance from deformation. Likewise, if you're trying to figure out what the velocity is going to be, and this is our kinetic energy, when we try to actually figure out what that is, we want to measure that as it passes the origin or as it goes the opposite direction. So you'll see that we're measuring from x equals 0 for this particular part. And then that just kind of a brief discussion on how are our springs working, where is the kinetic energy involved, and where is the potential energy involved. Remember, the potential energy is all before the motion occurs, and then once the motion starts happening, the kinetic kind of comes into play. Now remember, we're talking kinetic and potential can be conserved, one side versus the other. All right, from there, we can actually do some really intense derivations to figure out this particular thing. And this is, what is the maximum velocity of the oscillator at any point during its motion? Okay, so that's our formula for Vmax. This is going to be, again, a maximum. It's going to depend on a few different factors. It's going to have a direct proportionality to the amplitude or the distance from the 0 point. Remember that x is the distance from deformation. I'm sorry if my handwriting is atrocious. I do apologize. And then we have K, which is going to be our spring constant. Again, this is going to have to do with the material that's actually being used to make the spring, as well as the shape of the spring. And then we have obviously the mass. Now this is different from a rotational version. And this guy might actually look a little bit familiar to you in that it looks a lot like what we were talking about when we were talking about pendulums, because this is going to be the rotational version. So again, we take our known variables for our linear versions and we convert them to rotational quantities by doing a few different things. Okay, so let's do a practice problem. For this one, we're going to calculate Vmax by taking the square root of K over L. Oops, sorry, not L, M. Wrong one. And then we're going to multiply the whole thing by the deformation. Okay, so for our particular thing, we have the mass of the car, we have the force constant K, and we were given the actual deformation is 0.1 meters. So we're going to plug these values in, and we should get remember, mass should be in kilograms, so it's already pretty good. We're going to multiply the whole thing by 0.100 meters. And we're going to get that the maximum velocity, and this is assuming no damping. We'll talk about damping in section 7. It says the maximum velocity of the car on the bump is going to be about 0.0, I got 0.852 meters per second to calculate that one. All right, and with that, we move on to section 6, and this is just going to be a discussion on uniform circular motion. So this first diagram is an example of a type of uniform circular motion, and one of our goals in this section is going to be to describe how can we figure out what the period of a uniformly rotating object is, not to be confused with the period of a pendulum. Remember, pendulum does not make a full circle, so that formula that we discovered for that period of a pendulum does not apply here specifically. All right. So first thing that we want to notice is that there are a lot of things that actually do perform this, quote, uniform circular motion thing. Now, what we're looking at here is this thing that is rotating, and it's causing a shadow on the ground. And as it does that, if you look at this thing rotate, so imagine this thing going around and around and around and around, and doesn't stop, and it just keeps going. Well, these lights that are shining down are all shining down at about the same distance from the ground. As this light goes around, this little part moves itself, right? So let's say it's over here. When it's over here, it's going to cast a shadow here. When it's down here, it's going to cast a shadow here. When it's all the way over here, it's going to cast a shadow on the outside. So the shadow tends to move, right? And as it moves, it goes back, forth, and so on and so forth. So we can take a circular motion and we can actually simplify it into a linear motion if we want. Now, in doing that, we're going to have to know a few things. So first thing to know is that we're talking about uniform circular motion again. We want to make sure that what that means is that we're talking about a point P on the outside of a circle. And we're looking at how fast it's moving along the circle itself. Now, we're not going to do the derivation. We don't like derivations in this class. And derivations don't really help you understand exactly what we're trying to get to. Unless you're really, really interested, which absolutely please read through the text for it. But derivations are not something that are actually discussed on the AP test, which is why I don't do them. So just to kind of give you an idea of what we're looking at this point P projecting a shadow. So if you imagine like a path down here, if we showed some lights down, just like we saw in that previous diagram, as this point P moved along, the shadow of point P would change from position, and I'm just kind of eyeballing it, from position to position. In the top half of the circle, we would see this thing move this direction. Once it got down here, we'd see it move backward. So this is the top half, and this is the bottom. Okay, so if we wanted to, that is one way that we could actually track the circular motion, and we simplify it into a just simple bouncing back and forth, aka a spring. Think Hooke's law. Now, Hooke's law comes into play a lot in this particular chapter because it basically just describes what happens when something bounces back and forth, and that's exactly what one oscillation is. All right, so again, we're back to this diagram. Now, if instead of just tracking the dots on the ground, we started moving the ground at a constant rate, you're going to see, guess what? A wave. Oscillation is a shorthand. This is like the 2D. Oh, wait, no. Maybe this is 1D. I'm not good with dimensions. All right, so this is the one-dimensional version. The two-dimensional version is going to be a wave. Pretty cool. All right, moving on. We just have this one formula to talk about, and it's the period of a simple harmonic oscillator. So this is a circular motion / a spring / an oscillator of pretty much a lot of kinds. Okay. Now remember that in our pendulums, we have to simplify this quite a bit, in that when we actually are dealing with a pendulum, the only thing that matters is the length. And we talked about why in previous sections. Okay. And that is all. Next section talks about damped motion. So think, we've been dealing with non-frictional motion so far. Now we're going to add friction in, and that's what we're going to call damping. Thanks.